who can access the chat, whether everyone or only the ones who have subscribed. But anyway, if you can write in the chat, please let me know that you can hear me. That would help. Okay, so today we are going to talk on segment trees. That's a bit weird. I thought I have started it. Yeah, it should be it should be visible. I can't. Uh, okay, I think let me take some time. I'm not sure. Yeah, Vinitha, Saptarshi here. I have started the streaming with that stream key, but I opened the link on mobile. I can't see that the video going on. Can you check? So okay, so it's getting streamed. Oh, okay, okay, cool. Yeah, currently I'm muted so that I can speak to you. Mhm. Okay, okay, sure. No. All right, I think you can hear me. Let's check this. Mm, it's a bit strange. I don't know. Can you confirm if you can hear me? Because can you guys see and hear me? Because I can't actually find that. Hmm. Okay, okay, great, great. Thank you. So today we are actually at the second session of segment trees. It's nice that you can hear me, and it's an exciting point of time because we are now going to see the best what we can do with segment trees. Of course, not we are not going to delve into too much of depth. We are not going to see the most difficult topics today, but definitely we are going to take some leaps ahead of what we discussed yesterday. So, talking factually, we'll be talking on lazy propagation, we'll be discussing sparse segment trees, we'll be discussing certain problems, and then I'll be focusing on certain other concepts, including merge sort tree. That's basic agenda for today. If you have any questions, it's 5:38. We'll be starting at 5:40 or 5:41. Starting at 5:41. If you have any questions regarding today's session or regarding any of the previous sessions, please do ask at this point of time. I'll be happy to receive the questions. I hope you all can hear me, and I hope uh, you all are prepared for this session. So, any questions till then? Any questions till then? Please do ask. So I think before proceeding into the topic, I am Saptarshi Mukherjee. This is the fourth session I'm taking in this DSA series. It is a series of advanced topics, and we started with tries. We proceeded through binary tries and character tries, and then we have come to segment trees. This is the second session on segment tree. I have taken earlier sessions on behalf of Unacademy, both on Unacademy platform as well as on YouTube, and this is probably the first time I'm teaching segment trees on behalf of Codechef team. So anyway, and apart from that, I've graduated from IIT Bhilai, having pursued BTech in Computer Science and Engineering, and currently I'm working as a software engineer at Google. So that's pretty much about myself. We'll be starting at 5:41. If you have any questions, please do throw at this point of time. I'll be happy to address them. So the prerequisites for today is yesterday's session. Basically, whatever we discussed around segment trees, the basics around point updates and range queries, how the segment tree helps in doing that, basic idea about how the time complexity analysis is optimized for our requirement. Those are only the prerequisites. If you have understood them, you are good for today's session. Again, I'll write down the agenda. We are basically going to cover lazy propagation. We are then going to cover certain other concepts like sparse segment tree. The third topic, or basically after this, we are going to see some problems. We are basically going to solve some problems together. And then we'll be looking at something like this, binary search on segment tree. You will see what this means, how this looks like. And then finally we will shift to merge sort trees. Good enough? These are the 5 topics that we'll be seeing today, quite many in terms of number, but they should be, like, you should be comfortable with all of them by the end of the session. And the only prerequisite is the last session, previous day session. So if there are no doubts, then let us proceed. Keep the comments coming. I think that will help us flow faster. That will make it more productive. Okay, so we will start with lazy propagation. So for lazy propagation, let's start with the classical problem. The classical problem is given an array. Okay, I just checked if I was audible. Given an array of n integers where ai is basically from 1 to 10 to the power 9. We want to perform q queries, some q queries, and each query is of this form, either of the first type, which is basically one LR, where we say that tell the sum. This is range query. You have to output the summation of values of ai where I ranges from L to R. And the second category is where you have to update some range. You have to say that okay, from L to R, I want to add the value val to all the values. I want to add this value val to uh, all the indices in this range. So for all I belonging to L to R, you basically need to do a of I plus equals to val. Good enough? Is the question clear? I hope the question is clear. So these are the two operations. N ranges to 10 to the power 5, Q ranges to 10 to the power 5, and both are positive numbers. And now you have to solve this using whatever data structure you can think of. Since the topic is segment trees, we'll solve it using segment trees. So try to identify what is the difference. This is a simple range query. So we are asking for the summation. Instead of summation, we can also ask for the maximum, the minimum, and whatever we have done in the previous class, we can ask for any of them. We have now known that they are at par. Like all can be done with the same kind of ease. But this is kind of a challenge for us, and we'll discuss how we can do it differently. First of all, try to think about it for some time, and then come up with the idea that if we create a similar kind of a segment tree, a similar kind of a sum segment tree, which starts with some root node with an index 1 and then proceeds to 2 children and then proceeds, and basically we know that at the last level we have only leaves which correspond to the array elements themselves. When we have the same structure, and now when I say that okay, now you have to update these indices L2R in the array, you have to update these indices, these elements, you have to update them, you have to increase each of them by value. How many nodes in this? You can say in amortized manner, you can say a direct figure, you can tell anything. You have to give me some approximation at least, that how many nodes do I need to update. If I increase every value by val, how many nodes definitely will get updated. So that is a kind of lower bound for my time complexity analysis. And in some way that is also the approximate measure of how much time is consumed behind one update operation. So the question is, when I want to do one update over here, how many nodes are going to get updated? Let's have some answers before we proceed. So in case someone has joined very recently, if one operation of this kind takes place, how many nodes shall get updated? In our segment tree, if we form segment tree just using our simple concept, there are n integers. So at the leaf level, at the last level, we want at least n, and then on the previous level we'll have n by 2, n by 4, and so on up to 1. This is the basic structure. So if this clarity is not there, it will be quite difficult to proceed. So maybe if some of you can guarantee that you are getting the idea, and try to answer this question, how many nodes shall get updated? Should I give any options? Will that be easier? And yes, if it is subscribers only mode, means only those who have subscribed can actually their messages are only viewable to me. So you can subscribe the channel so that we can have a better interaction. I'm sorry. Oh, I see 1740s. I'm sorry, I missed these things. I should have opened it once again. Okay. So according to the question, have you got placed? No, I appeared in it off campus. That's how I got placed. Thanks, Hitesh. And yeah, segment tree with lazy propagation. If we are using lazy, then at most 4. But if we are not using lazy, that's precisely the question. If we are not using lazy, then how many operations shall be consumed? And how did you say 4? I didn't specify what is the value of n. That's interesting. Suppose your let's I hope you get the idea. So if this is your segment tree, over here also we have other things. R minus okay, great. R minus L plus 1 into log n nodes will get updated, right? Quite interesting. And why such an answer? It would be interesting that we want to update how many nodes. We basically want to update some range of the leaf nodes. And what is the range? We know that range is basically R minus L plus 1. Given this range, we know that if I am changing this particular node, then all these ancestors are going to get updated because each of them contain the range sum. So all these ranges are getting affected. Hence, for each of them, there is a log n factor because log n is precisely the number of ancestors we'll have, and hence we will have something like this R minus L plus 1 multiplied by log n. Very good. And we understand that, okay, the kind of intuition that we used while forming the segment tree was every operation, whether it be update or query, has to be in log n time. हर एक ऑपरेशन log n time में होना चाहिए था. But now what we notice is that a single update operation is now depending on the values of R and L, and this is basically something of order n, which means that when it gets multiplied with a log n, it is basically order n log n per update. And if it is per update, then this basically amounts to q into n log n, which is way too high because this part amounts to 10 to the power 10, let alone this part. Okay. So this gives us the idea that somewhere the number of nodes which are getting updated is quite large. Hence, if we make it a kind of habit that whenever we are updating, after updating, all the nodes need to have the perfect value, then it is a problem. If we make up our mind that, okay, all the nodes should have the perfect value after an update, then definitely that kind of a structure will take a lot of time. We cannot use that. Hence, instead of changing the structure of a segment tree, there is another way of going over it. We know that whenever we are querying over any range, definitely order log n nodes are going to be queried. During a sum query. That is, we are querying what is the sum of these nodes. If we know this, what we basically know is that if I'm actually going to do so many updates in one go, I won't be requiring them in the immediate next operation. So somewhere I can actually optimize this. I can say that, okay, it is not important right now to pass the values downwards. If at some point of time we can say that, okay, this node is going to remember something, it will not pass on the information. Later on, when required, we will be passing on. When our query, which is a sum query or the max query, is going to ask from a node that what is your value, it is only at that time that the node needs to know its value. Before that, we should not worry about updating all the nodes. Rather, we should store an information which can tell that, okay, this is the symbol of what should be added to all these nodes or what is pending to be added in all these nodes. This is the idea. And hence, this is what we are going to see. In lazy propagation, the way we apply it is basically the push operation. What I mentioned just now is the intuition behind push operation. Push operation tells that in case this is your structure of some part of the segment tree, there are other parts as well. From over here you have other nodes as well. Suppose this is a certain part and you know that all these 4 nodes are involved in the update operation and all are getting updated by val. And you know to reach all of these nodes you require log n time. It essentially means that this node, which is the sole entry point to all these nodes from the rest of the world, you cannot come to these nodes without visiting this node. It can contain the information that, okay, all my children or all my nodes in my subtree, they must be added val. It can contain that kind of a symbol that whenever you are supposed to or you require to go down, remember that whatever you are seeing below, you have to add val with it. This is something that this node can remember. And this is the logic that we'll be applying. Something like this basically. So what can we say from here? Yeah. So again, the intuition or the idea that we are applying over here is that when a node is getting fully covered, we don't immediately require to cover or to visit all its children. How will that help? Suppose I am like stopping over here. I am saying that these nodes won't be covered. Let us take an example. So let us take a full-fledged example. Had it been an offline class, I would have asked you for the values, but I know that all these lags and things will not allow that to happen. So anyway, these are the values we have: 3, 1, 4, 2, 5, 3, 4, 1, something like this. We have 8 values. Next, what we know is by taking the sum, we basically have 4 over here, we have 6 over here, we have 10 over here, we have 8 over here, we have 5 over here, we have 13 over here, and we have 23 over here. If we do our n sum, it will work as usual, no difference. Now, suddenly I want to change this particular part. I want to change these nodes. Okay. So what can I say from here? I can say something that okay, if you have to change these nodes, let us proceed to change them. Let us see how it goes. It will say that okay, I'll go over here, I'll go over here. It says both are covered, this is totally covered. It says this is totally covered. So we will say now no need to go to your children. No need to go to your children. Suppose this operation was add 3 to all the nodes. Which means that basically we want to add something like this. We want to add 3 in a lazy manner. We want to add this in a lazy manner to all the nodes which are lying below, and for this node also we know that the value will get changed. We can say something like this, that update your value to 13 plus 3 into whatever number of nodes you have. So it knows that there are 4 nodes, so you can say okay, 13 plus 3 into 4 is basically 25. This is my own value. This is the value of this node. Any doubt? This is the value of this node. Why? Because within the subtree you have basically 4 leaves. So that is why it will get incremented by 3 into 4. How can we find out this 4? Will you go to the leaf level to find it out? Definitely not. You will just use the values of TL and TR which we discussed. That is just the range of this node. LR, L dash, R dash, whatever you remember from yesterday. We are just going to use it and it is just going to be TR minus TL plus 1. Got it? This will give us this value, but one important thing is that the lazy thing is not getting updated immediately into these things. What do I mean? That ideally this value should have got updated to 5 plus 3 into 2, 6, which is 5 plus 6, 11. This should have got updated to 11. This should have got updated to 14, right? But they are not getting updated. Make sense? All these nodes should have got updated, but we are sort of storing something so that that operation does not take place immediately. This is called the lazy step. Any doubt till now? Right. So now we are maintaining at every node, we are maintaining two structures. Tree of x is equal to the value of node x, and lazy of x equals to the value that needs to be added to every node in the subtree. To every descendant, we could have said, and not only this value, this is not the exact value that needs to be added, but proportionately. If we are at the child, then that needs to multiply it by r dash minus l dash plus 1. But this is the value that it has not informed its children. So this is the value that it has not informed, x has not informed its children, 2x and 3x, 2x and 2x plus 1 yet. Great. So now getting into the depth of it. How will it act now? Now if I ask that, okay, I want to find the sum in this particular range. I need to find the sum in this particular range, or maybe I need to find the sum in this particular range. Okay, how will it behave? It will tell me, okay, let us come down. We'll come down from here. We'll come down over here. I will see that this is fully involved, so I will take 6 from over here. Good enough. I'll take 6 from over here. Okay, I'm sorry. So over here, I forgot to do the update, I think. This will get updated. In the previous operation, this got updated to 5, and it was a normal update operation. 5 means 4 plus 5, this will get converted to 9. This will get converted to 13. This will get converted to 13 plus 25, which is 38. Usual kind of mechanism. When you go upwards, you are doing the usual kind of mechanism. When you are going downwards, you are a bit cautious. That I'll go downwards only if I am not totally covered. Only if I am partially covered. Again, the same kind of logic that we did in case of range queries. We are using that optimization that only when we are partially covered, we should go down. As a result of that optimization, what we have is two things. One is tree, another is lazy. Tree means what I know for myself on the basis of what my parents have informed me. And lazy means what I have purposely not informed my children, but I myself know. Okay? This is the usual definition. If you want to hear again, you can maybe slip back or you can ask again. But now what we are interested in is, now we want to query this particular part which I have marked with this red rectangle. So let us see how this goes. Now see, these two values are not the correct values. These three values are not the correct values. Why? Because of this lazy part. It has not informed its subtree that this is the value I want to add. So when you are computing the sum, it is your responsibility to take into consideration that addition. But the problem is that you cannot take the sum right from here. You have to go to this level. Why? Because this node is not involved. You need to go to this level to get hold of this. So let us see how it works. The way it works is something like this. You come over here, you get the value 5. So you have got the first value, which is 5. I'm sorry. You know these two values are involved. So this is the node where you stop. You start from the top, stop over here, you get 9. So 9 is the first value, then you go at the top, something like this. You go over here, or maybe I can use the highlighter. You go over here and then you come over here. Is this yellow visible? This is a highlighter that I'm using. Maybe I can use some other color. Okay, this one. You go over here and then you're going to come down. When you come down, you know that this guy is not fully covered. Because it is not fully covered, because you need only a part of it, what it will say is go to my 2 children. Okay? And when it says go to my 2 children, it will do the step that, okay, I have stored something which I have not informed my children. Because you're visiting my children, go and inform them. With this, what are we ensuring? That we were, according to the policy of the range query, we are already visiting that node. So by passing this lazy thing and by asking it to add it to itself, we are just doing twice the operation. We are not changing something from order 1 to order n by 2 or root n something or log n. What we are saying is that when you're going, just add it over here. So it will say that, okay, plus 3, just add it over here. So this will convert itself and this will convert itself. That's basically how it occurs. So let me first complete it. We will visit over here in this, we'll visit over here, then we'll come back, then we visit this. Then we say go over here and go over here. First we go over here, what we say is this is sufficient. So this guy does not need to pass its things to the bottom till now. It is a matter of convention whether we pass it or not. But till now it is not important. It can come above, it can use its own value. And over here it will say now I need to depend on my children. So okay, it will basically pass it. And from here we can fetch the values. This is the value that we are interested to fetch. So we can take the value from here, we can take the value from here, and we have the value from here. These 3 values can in total altogether give us the required answer. So what shall we get? We'll get something like this. Let me switch to the pen. We are going downwards. What we'll see is that this lazy part will get transferred. So it will say that, okay, I am now informing my children, so forget it. they will now remember that okay, we have plus 3, they have got to inform their children at some later point of time, so they have stored it, and they will convert it 8 to 8 plus 3 into 2, which is 14. Why 8 plus 3 into 2? 8 plus the value that is going to be added times the number of nodes within it, which is r minus l plus 1. Similarly, we'll have for this, we'll convert 5 plus 3 into 2, 6, which is 11. Now what do we have? This is sufficient. We can take this value, this is 14. So we can have 14. And the next thing, we can go over here, we can say that okay, this is not fully covered, so you have to visit the children. When you're visiting the children, cross it, do a plus 3 over here, do a plus 3 over here, and pass it. So when you're passing it again, another thing that is left out is this needs to be converted to 7, this needs to be converted to 4. Now look at this. 7 and 4 are the values which that update had left it at. So now we are actually realizing that update. जो अपडेट पहले हो चुका था +3, वो अभी हमको पता चल रहा है कि ये +3 हुआ है. Alright. So, but we did not require it till now. Now that we are requiring it, we are coming down. Over here, till now we did not require it. We know that these elements have also got added by 3. But we have not added it till now because they have not been required yet. So is the idea basically clear? Don't worry about time complexity analysis, but is the idea clear, and can you map it with the range query that we discussed? That when are we going down and when are we not going down? I'll show the coding implementation and that will probably provide much more clarity. But till now, at least intuition wise, is it clear? Now this is again a method of a matter of convention. This +3, when should you be passing to the child? You can pass it to the child. Great. The rest as well, you can keep on writing in the chat. So you can pass it to the child whenever you visit this node. So whenever you're coming to this node, you can say that okay, pass it to my children. Then also you can say that okay, whatever is the number of nodes visited multiplied by 2 is the number of operations, extra operations that this range update is causing to me. And that is totally, in terms of asymptotic time complexity, there is no difference. Another convention is that before going to the children, when you're going to the children, when you know you have to go to the children, then only do pass it. So you can actually make it it is totally up to you. You can see what you can do with it. There is absolutely no force in regard to it. You can pass it beforehand, you can pass it later on also. So that's pretty much the idea. What is a time complexity analysis, or what is a time complexity? What is the number of nodes? Just to revisit from yesterday, what is the total number of nodes in that segment tree? Total number of nodes, which actually is a space complexity. You can actually say in big O terms, all of you, what is the total number of nodes in the segment tree? So there is also something off topic. There is some snack down related discussion or session that is going to be held again on some advanced topics tonight at great. So order in. So tonight at 7 o'clock, 8 o'clock. At 8 p.m. we are going to have that, so you can attend that. You can get valuable insights over there. I'm not sure about the exact content, but if you are interested, then try to attend. So we'll not be extending today's class just like the previous days. So number of nodes in segment tree is order n. Update operation is order log n. The query operation, it is the same. The query operation is the same, it is order log n. What is the update operation? Time complexity. What is the time complexity of the update operation? This also turns out to be log n. Why is it so? Because if a node is uncovered, or totally covered, then we are not going to visit its children. We are going to visit the children only if a node is partially covered. And according to the same logic that we used in range queries, the total number of nodes that can be partially covered at a certain level is 2. maximum number of nodes that can be partially covered. If there are two partially covered nodes, which basically looks something like this, that this is covered towards the right, this is covered towards the left, then basically we can say that there are two children at the maximum. There are two children for each of them which are important to us. So what this means is that the number of nodes at every level where we are visiting is actually 4, which means that during our push operation or during our update operation, again we'll be using a similar kind of a strategy. We'll follow LR in the same manner. The only difference is we'll be using a push array where we'll be making changes in the similar manner as we do in the segment tree array. So there is a tree array in segment tree where we store the values as per the indices that I had shown yesterday, 1, 2, 3, 4, 5, like 2x and 2x plus 1. Similarly, we will do exactly the same in lazy array also. So there are two arrays we need to maintain, tree and lazy, and because both work together, there is no separate time complexity analysis required. It is exactly the same as the query operation. Even in the query operation, okay, so another thing is that there is a push operation that I mentioned, which this query operation shall be using. Not only the query operation, suppose after an update I choose to do another update. So if during that update I see that okay, I'm passing through a node where there is some lazy component, so over there also I can, this is totally a matter of choice, you can take that value which is waiting over there and you can pass to the children. Because you are visiting a node, now you have the full authority over passing it to the children. Because the reason we were not passing it downwards is because we were not visiting them. But now because you are visiting them for some other task, without increasing the time complexity, you can utilize the push operation. So push operation, what is the time complexity? I hope you will agree with me that it is order 1 operation. What is this? Simply when you are at a node and you are storing some, you have stored some lazy thing and now you want to pass it to its children, you just have to pass this lazy thing over here and this lazy thing over here, and then you need to convert this to 0 because now there is nothing waiting for the children. To both the tree and the lazy you need to add this value. Why both? You need to add to the tree because yes, the child now comes to know about it, so it should update itself. And what else? You need to know, the lazy needs to know it because the children of this guy have not currently known it. So the lazy of this node should now become aware of it. So does that make sense? I hope so. Else just pour down the questions that you have. I'll be switching to the code. And today I will not be, I hope this is visible. Today I will not be showing from my own code. This is a code library that I found just today from some post. And the codes looked good to me. So I'll be basically covering from here. If you have any doubts, again, just the same way as I was discussing the previous day, I have enlarged it. So ask by using the number line. I hope the number lines are all visible, right? So ask from here. This is someone else's code, but again, same kind of strategy or procedure. Cool. So the same kind of thing what I was doing using merge, he is doing using combine, but he has not done consistently. Anyway, let's leave that. So okay, in the build operation, as you can see, here also we are okay, I'll come to this later. Let's discuss the things which are different. Here we are at the update operation. We want to update from I to j. Yeah, we want to update from I to j. What is B and E? These are the limits of the node. B and D are the limits of the node. So we can say that, make it easy. This is our node. So this represents from B to E. B stands for probably begin and E stands for end. Okay, beginning of a node and end of a node. Now we have to search in this particular range I to j. And we'll do something like this, that if B and D are totally lying within I and j, then we can basically set this lazy, and what he has done is he has pushed it immediately. So we have set the lazy over here, and by pushing, what he is doing is Let us look at the push code. The only thing that it is doing is an order 1 operation, which is that if it is not equal to 0, then the tree node Tn is basically the tree of n, tree of x from yesterday. So tree of n is getting updated. This is nothing but tree of x plus lazy of x multiplied by r minus l plus 1, the same thing. And then what it is doing is if it is not a leaf, then it will let its children know about this lazy part. It will say that, okay, now my children should come to know about this lazy part. So here the lazy indicates something which even this node is not aware of currently. This node, like when you are storing this lazy over here, it is not aware of, like the tree array is not aware of this value v. Only the lazy part is aware of it. So here lazy indicates that value which even I don't know. So when you are passing it to tn, what you are doing, you are converting lazy n to 0. Any doubts? Just throw on me. Any doubts till now? Just throw at this point. In our convention, what we said is, and you can also find codes based on that, what we said is that for a node, update lazy and tn together. What this guy has done is something like this. When you are updating it, when you have reached this node and you are going to leave it because it's fully covered, you will update the lazy and then you will push from here. Whenever you do a push, what you basically say is that, okay, I'm going to pass it to the tree value of this particular node, and I'm going to pass it to the lazy value of this particular node and to the lazy value of this particular node. Okay. So these are the three things. Whenever you do a push, these are the three things. This is also a push operation, a push operation, push operation. One push operation will basically shift the value from the lazy to tree value of this node, lazy value of the children. And what will happen? This lazy part will get converted to 0. Okay. Now this is something you just need to know for the first code. After this, when you have practiced on one code, you can use that template everywhere, and then you don't need to look into this code. It will happen just automatically. You don't need to strain too much into it. So understand it once, apply it 100 times. That's basically the beauty of these structures. So what he has done, if there is nothing, if there is no such lazy thing, then just return it, because you don't need to waste your time now. Else, we are not doing it recursively. This is one important thing. We are not doing it recursively. That push from here, then push from there, and then push from there. Only add it over here. Alright. So we are updating tree, we are updating lazy of the child, we are updating lazy of the other child. Now coming back, what are we doing? We have, let's see, what are we doing? Okay. So when we have updated it, we are then pushing it. That's fine. This part is totally optional. You can totally omit it. Even if you omit it, this won't actually cause a problem. Why? Because later on you will be pushing it at any other point of time. So it's not a problem. Now let's come over here. What it is doing is, if it is not a leaf node, what you will say is update it. So update the two parts. And now it is in the case of partially covered. So if it is uncovered, then it is going to return. This is the part, uncovered. If it is fully covered, this is the part. If it is partially covered, then this is the part. Some very good optimizations that this guy has used is the use of bitwise operators. You can see this particular operator, what it does is finds the middle element. Same convention that we had used yesterday. We had divided, if we have 6 elements, we are divided into 3 and 3, not 4 and 2. So he has used the same convention, but using bitwise operator, which is according to computer architecture quite fast to implement. Then you have these two updates, and then it is going to pull it. Pull basically means that Tn is equal to T of Lc plus T of Rc. Something like we were combining from the two children. He has done this pull operation by which you can directly take in the values. Makes sense? Okay. So after that, whenever you're updating, this is one important thing. Before doing anything, it is pushing it. Why it is so? Similar to what I told you, whenever you are visiting a node, you can do that extra push operation, because that is of order 1 complexity. So that is what it is doing, and even in query, that is what it is doing. It is slightly unconventional to do both the things, this push and this push. I've not seen many people doing it, but again, totally optional, doesn't make any difference. Absolutely. But this part is a standard, this part and this part. These two things are a standard. At the beginning of update and at the beginning of query, I will let my tree value and my children know about what value I'm holding that these guys don't know. Okay. And the query, you can see it's absolutely the same thing. We are going to push and then we are going to combine. That's it. Whatever I was doing using merge, it is doing using combine operation. And how is it doing it? It is basically fetching this value and it is fetching this value. And it is combining it. Any doubts? Till now, are there any doubts? We started a bit late, but I think we have safely covered 30 to 40 minutes. I did not expect so initially. But do you have any doubts or anything that you want to cover? You can see both have been defined in the same manner. 4 into n, 4 into n. This is t and this is lazy. In the same manner they have been defined. Alright. You can specify the line number and ask any questions. It's good to see that, okay, you have no doubts till now. I'm sure about it, I'm certain about it that you will get more clarity once you try it yourself. So I'll leave it over there. Next 1 or 2 minutes you can ask any questions as we move forward. So what are the good things that he's using? First of all, right shift by 1, which basically stands for division by 2. Even that integer division, that same thing, it actually preserves. If there is a, uh, anyway, that's slightly off topic. So great. Let's proceed to the next topic then. The next topic where probably we don't have a code over here. So I'll be sharing some part of it myself. We'll be looking at sparse segment trees. Where are we? Over here. Yeah, we don't have that. Anyway, so we'll see it over here. Sparse segment trees, but without going into it, let's first discuss the problem. The problem goes something like this. You have entirely the same thing, n numbers, same constants actually, ai less than equal to 10 to the power 9, or mod of ai you can say, n less than equal to 10 to the power 5, and of course it is positive, q less than equal to 10 to the power 5, I'm sorry, so the difference, I'm sorry about it, the difference is that n can go up to 10 to the power 9. AI can take any value, but initially AI equals to 0 for all I. Okay. N can go up to 10 to the power 9, Q can go up to 10 to the power 5, and this is the case, and these are the queries. What have we seen? We have seen one pose value. So we can do a point update kind of operation. You can also do range updates. We are going to see how we can tackle with this large range. Next thing is, suppose we want to see 2LR. In that case, what can we do? 2LR means find out the sum. We have to find out the sum or max, whatever. Okay. And whenever we say val basically means that a of pos will become equal to val. Plus equals to val is also equally easy. But anyway, we'll focus only on equal to val. And val is greater than equal to 0. It's not necessary, but okay, we are having this for the time being. So the question is, and val is less than equal to 10 to the power 9. Now how can we perform this? The problem we first of all face is, we know that uh, all the nodes can have a value 0. So we don't need to go to every node and say, no, you need to increase to certain AI. No, we don't have so many AIs, and we also know so many AIs we won't have till the end. So we basically have to allocate some space. Everyone has to get zeros assigned to themselves, and then we can do the normal operation. But the problem is that even allocating the space is also not feasible. If we say something like tree 4n, that is not something feasible because 4 into 10 to the power 9 cannot be the size of some array. Keeping that in mind, what can we do from here? Basically, we can say that just keeping the time limit in mind. In 1 second, you cannot create an array of 4 into n length or even n length. So, what can we do possibly? Especially basically, if you want to initialize always zeros, it is not possible. Basic thing is definitely, it can be possible. So, first category is suppose that I've given you all these queries beforehand. And then I've asked you, whatever you have of this category, print the answers for them sequentially. So if there are suppose 10 to the power 5 queries, out of which half are this category, I'll tell you, okay, you perform at your own convenience. I've given you all the queries. By the end of 1 second, give me the answers of all the sum queries. Can you use some easy technique by which you can evade this possibility of having so many values together? Is there some possibility to evade it? What can you exploit? If I want to say that, okay, use the same structure of arrays, but I don't want to create so many spaces in the array. I don't want to create so many nodes. I want a kind of optimization. So can you help me there? Again, L and R, I want to be very honest about it. L and R means L and R. It can range, L can be 3 and R can be 3 into 10 to the power 8. Okay, so you have to tell whatever values are there in this range, summation of that. And I don't want to keep order n nodes. But again, I don't want to change the basic structure, the basic way of proceeding. What probably can we think of? What can we try to exploit? What do we know that it is finite in our case? So it turns out we can store frequency in sec tree. We can store frequency, but frequency of what? How many pose values are possible? We know pose values, it can go from 1 to 10 to the power 5. Okay, q less than equal to 1e5. Fine. Which essentially means that if okay, are you thinking of sorting the queries? Are you thinking of tackling the queries in a unified manner? That on the basis of one query we can think of transitioning to another query? That is slightly beyond the requirement. We don't need to actually bear that problematic situation. One rather easy observation is that my pose value, which is basically the problem, this can go from 1 to 10 to the power 9, right? It can go from 1 to 10 to the power 9, this pose value. What I can ensure is that instead of storing all the pose values, if I think about how many pose values will ultimately come, because these are the pose values which are going to have positive values, rest are zeros, totally unimportant to me. I don't require the other values. So suppose q is equal to 3 and n is equal to 10. You know that only these many, a maximum of these many array elements will be positive and important to me. So if I say, okay, what are the pose values? You can say that, okay, pose values are something like this. 2, 4, 9. Okay, these may be the pose values, position values. So what I can say is, instead of storing such a large thing, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, what we can say is, because this one and this one are important to me, I can just take this and store it. I can just take this, I can take this, and I can take this. And yes, I now have an array of 3 elements. And I am not losing anything. I can store it, I can say that, okay, it is like a 2D kind of a thing, maybe, where it says that, okay, I am involved in storing only three, there are only 3 positions that are involved. The first one is at index 2, the next one is at index 4, the last one is at index 9. And these things, whatever like the values are, I can copy them. I can tell, okay, this is A2, this is A4, this is A9, that's it. And I can store just this data structure. So if I know initially that what are the post values, I can take them, then I can form my own structure based on that. I can sort these on the basis of this, or I can use some map. I can say, okay, these are the number of unique values. I have k number of unique values. So from 0 to k minus 1, I can form an array with all these indices. And in each place, what do I know? The frequency, if I store, then I'm done basically, because whatever elements I've omitted, I don't require them. Now, if suppose I want to search from 3 to 8, what will I say? Do a kind of binary search. So I'll get 3 somewhere over here and 8 somewhere over here maybe. And we are done. So we'll basically get this element only. So kind of binary search is going to tell us, okay, what is going to be the summation, right? And forget about binary search. We can do a simple kind of, segment tree operation. So while we are storing it in segment tree, we can store it in the node 0 to k minus 1. So we will have 0 to k minus 1 in the lowest level. And whenever at a node we want to see, basically what we can do is, whenever we are given some LR in our range query, we can find out according to this array, what is our L dash R dash. We can find out that what is our revised L and R. That we can search in our segment tree. There are other methods as well. We'll go to every node and there we'll see that, okay, the map value by searching, like we can do a lot of things like that. I was thinking about storing max value. We can get after all queries and storing in array and normalize the array. We can retrieve the original value. It would be quite complicated implementation, right? Quite complicated. For this, what you have to do? Let us talk in realistic manner, not in a imaginary fashion. What you basically need to do is something like this: collect the queries, store it somewhere. So whatever you have, maybe all queries, you will store all queries in some data structure. It will be a kind of vector. Okay, you can use some kind of vector over here. You can use 3 vectors also. One vector will just be a pointer to either of the 2 vectors, which is query or update. You can ask me in detail what do I mean by it, but you can figure it out for yourself. I want to basically store the queries. Then what I'll say is, whatever update operations, whatever update values of pause you get, collect all those pause, and according to all this, sort all those pause. And maybe if you have something like this, 2, 3, 18, 21, 30, then we will now re-index them as something like this. These are the new indices. Okay. Now we will read through all these queries. We will see that, okay, there is a pause. There is a pause 1 to 8. 1 to 8 means this is of the first type. The type is 1. That means this is update operation. At the second place, we want to put 8. How to find out that in the segment tree, where should I put it? I'll go to this map. This is a kind of map. I'll see that, okay, in the second place, I basically got this as my new index. So I'll go to the map and I'll say that, okay, update X, the way we were doing TL, TR, and pose and val. The pose value will be 0. The val will be this one, 8. Okay. This is going to be our operation. And then it will be similar to our initial thing. And similarly, for all the update operations, we'll have it. For a query operation, what shall we have? 2, maybe 3, 5. And it is important, don't do all the updates together and then all the queries. You cannot fiddle with the order. Why? Because the order is important to you. Whenever you say this, the answer for a query, you need to keep in mind only the updates that have been done till now. You cannot play with that. So this is important. And even when you know that the order has to be maintained, if you are allowed to read all the queries, all the update operations together, you can actually take the advantage of that by creating this kind of a map. and then everything else is easy. So what am I doing now? Okay, if you have to find out from 3 to 5, what will you say? Okay, go here and or maybe 3 to 50, or maybe 3 to something else, maybe 25, 3 to 25. What we can say is that, okay, 3 means this is the element that you can start with, 25 means this is the element up to where you can go. So we will see that 1 is the starting element, 3 is the ending element. So keys are sorted in tree maps. I think you know that. In maps, trees are sorted. So basically, you can use a tree set kind of a structure, or you can use even a sorted array. Also, you can sort an array and you can keep a hash map. Both are fine. Like either a map, or you can use a hash map, which is an unordered map, and a sorted array. But because you require the number of elements, from here, okay, you don't require the number of elements. You actually require only, yeah, the limits. So yeah. So in tree set, I can tell you in Java tree set, you will just have to use higher and lower to find out for this and for this. Okay, higher for this one and lower for this one. You will easily get it. You just have to check that +1 -1 kind of thing. In C++ also it should be similar. Okay, so where are we now? Is it convincing that this problem can be easily solved using coordinate compression? And this is exactly the code. Okay, I didn't code it. I thought I'll be coding it. But anyway, fine. I think this much is fine. You don't like, okay, for query, what will you find is, if you have got these limits, maybe y and z, what you can say is that query I'll do for x, t, l, t, r, and from y to z, something like this. Okay, x basically is nothing but the first index 1, and this is nothing but 0, and this is nothing but this thing. Or if we can call this m-1, then this will be m-1. Okay, for this map, the number of unique keys in the map. Clear? Okay, which is the situation? Now comes the interesting part. If you have any doubts, you can ask. Otherwise, feel free to answer, or maybe try to answer this question. What is the kind of situation where we cannot use this? What constraint, if applied on the question, or what particular character of the question will not allow us to use this particular process? Especially, to be very precise about the question, when can we not take all the queries together? When are we bound to do it in the exact sequence? That, okay, I have to do the query, then I have to do the update, then I have to do in the exact order that it has come, I have to do it. I cannot compute the next update and then together with all the updates. Like, when do I have to do something like this? That you have an update operation, you have a query operation, you have an update operation. So while answering this query, I basically before that cannot create the segment tree. For segment tree, I require this one. In which kind of questions can we not use it? Folks, we are running out of time, so maybe try to answer faster. Okay, so basically in case of online queries, when we have interactive problems basically mean that when you have an update operation, you need to, basically when you have a query operation, you need to answer then and there. Then only you can read the next update operation, then the next query, and so on. So basically, if you get this update queries later on, after getting this some queries, then the conclusion, or basically the takeaway from there is that over here you have to change the segment tree. Suppose now that this position does not exist in your segment tree, then that is a problem, and you don't know of this beforehand. So in these kind of problems, basically in interactive problems, it will not help you. Any doubts, or is it clear? In interactive problems, you cannot exploit it. And hence we move to some other kind of a structure where we say that now we cannot pre-assume all the different positions, so we have to create the positions, as we move forward. So what technique we can use? One thing is that which most of the students start with. They start with some kind of binary trees with like those node structures, where they say like some kind of a node structure is there that has a pointer, a left pointer and a right pointer. Not both of them are defined. There are so many things, but that is a pretty unconventional, or basically not a very efficient one. Efficient in sense like when you're using those pointers, it is not that easy to implement. In case of an array implementation, it is far easier. And then within that node, usually we save something like this. Within that node, we say what is the L value, what is the R value. So that is not a very nice implementation. Rather, we want to do something like this. We want to say that, okay, if I give you like imaginary thing is something like this. Imaginary thing is something like this. As if I have all the nodes. So we have to imagine that we have all the nodes. Suppose n is 8 or n is maybe 7 or 8. What should we say? Basically from 0 to 7 we have the elements, so n is n equal to 8. Just a second. Okay, fine. The n numbers, that's cool. So n is equal to 8, and suppose only 3 positions are getting updated. One is position, means pos equals to 2, 4, 5. These are 3 positions that are getting updated. If you mark it in the diagram, this is the position, this is the position, and this is the position. And yes, we actually create this kind of a structure, but all the nodes we will not create, because all the nodes means 4n, which is quite large, which can be quite large if n goes to thousands or 10,000s, or basically 10 to the power 9. We will say form only the nodes that are important to you. So for 2 we will say we have to form the node. So okay, form this root node first. Then you know that this is going from 0 to 7. So 2 should go in your left subtree. So form only the left subtree. It will form only this node. Then it will come over here, and then it will come over here, and it will save it over here. It can say, okay, now I have basically 2 marked over here. It will do something like this. Next we say, okay, 4. So we know that, okay, it will actually get 2, 4, 5. Okay, it's 4 over here, basically this one. So it will tell, okay, 4 lies over here. It will come over here, and then it comes over here. It is done. We have stored 4, 5. 4, 4. And similarly, when we have 5, it will basically come over here. We will come along this path, and this is the only node that we are going to visit as an extra node. No other node we are going to visit. So what this means is that these nodes we are not visiting. These nodes we are not visiting. And it makes sense also, right? Why should we visit these nodes? They are 0. In nature, they are 0. But whenever we visit a node and we see that, okay, there is nothing existing over there, we should keep in mind that we are not storing anything over there. And this is actually the concept of sparse segment trees, where we basically say, irrespective of the implementation, that now you'll be creating the nodes only those which you require, and they will be query based. So you face an update operation, you will create the nodes that are important to you, and of course update the thing. So when we are going to update some node and we see the node is not existing, make that 0 and then update it. That's it, simple. A node is not existing means that range basically has 0. So, and that is the reason, anyway, so that's it. Any questions till now? Now what we can say is, how many nodes in total may get updated. May get updated, basically green nodes may get updated to greater than 0. In this segment tree, see when I'm marking this one is also getting updated. Definitely all the ancestors are getting updated, but not other nodes. So what can we say? How many nodes in total may get updated to greater than 0? Oh, in this diagram we can see how many nodes are there. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 nodes. So when you have constraints in terms of n and q, and of course AIs, what can you say? Can we express it? Can we identify it in some manner the way we are doing it? What I'm doing is, for every query, if it is an update kind of a query, then mark that position. For that position you have to update it. So go to that node and update it the way you are doing it. If the node does not exist, or if any intermediary node does not exist, create it. Don't create 2 to right over here. We had 07 over here. Don't create 2 to right over here. You go to the proper depth, understand where you're supposed to stay, and all the ancestors should get created in the process. This is what we are doing. So can you answer this question? How many nodes in total may get updated to greater than 0? Kind of an approximate time complexity analysis or asymptotic complexity analysis it shall represent. Okay, so there are q queries. So every query means you are coming down. So how many nodes are getting updated in that step? A maximum of log n. A maximum of log n. These are the nodes that can get updated basically. So what is the total number of nodes whose values are greater than 0? Every query log n. So query times log n, q log n. This is the total number of nodes that can get updated. So can you confirm from here that at the end the segment tree will contain not more than q log n nodes? Our segment tree will contain less than equal to q log n nodes. Can we confirm from here? We can, right? Folks, please respond if you can understand. Is it clear? Or is it totally Hebrew? Like you're not understanding anything, just something is going on and you're just... Hi Lagnajit. I understand some of you might have joined very recently, but what about the rest? Is it clear? Or it is totally escaping your understanding? Okay, I'll take the silence as yes. I don't know if my chat is not getting updated. I hope that's not the problem. But anyway, so what this basically means is that the number of nodes that I'll be creating won't run out of, like memory space won't be affected by that. It would totally be in the capacity of my memory, and that's it. Would you like me to code it? Else we can move ahead. I had a few poll questions. Would you like me to cover the poll questions, or should I just move ahead with the theory? So let us see what the code can look like. One way of coding it is basically, okay, so I'll be coding it. Please do respond, else the same thing takes longer time and it's not optimized for either of us. So this is the kind of structure, and now what is going to be inside this? Simple, the same thing that we discussed, q login. This is what is going to stay inside this. And then we get something like this left, or maybe L. We have L, here is it's basically q into login, and R, which is q into login. So now what we know basically is we cannot create the indices the way we were doing yesterday, 1, 2, 3, 4, 5, 6, 7, 8 in that manner. That we were having something like this 1, 2, 3, 4, 5, 4, 5, 6, 7. Why? Because it may happen we are first creating these two, these ones, and then we are coming to this. So in some later query we are creating this. If that happens, then definitely and each of these things 1, 2, 3, 4, each of these things actually was storing a value for us, tree of x, or in this case the way we had it, I don't know where did we have it, segmentary or segmentary lazy, yeah, we had t of n. So here this n actually helps us in reaching the nth value, and we know n is less than equal to 4 into the total size of the array. So over here we can't do something like that. Rather, what we'll say is instead of x going to 2x and 2x plus 1, what we'll say is every node has a kind of id which is equivalent to x. It is equivalent. And for the left, instead of having 2 into id and 2 into id plus 1, we'll have something like this L of id. I like questions of the kind that why are we doing this, why are we doing that. So try to come up with all sorts of fancy or stupid questions, whatever you feel. Then only you will understand why we are doing which part. So LID is basically the index of this node, and RID is basically the index of this node. Okay. Now, how can we go to the left of this node? L of LID, something like that. Okay, nothing different. So if I see that okay, LID is not defined, what I know is that initially all these are zeros. Initially all are zeros. All are zeros. So if I know that okay, LID or L of whatever value I have is basically 0, that means nothing is defined to my left. I have to define it. So there are many ways in which you can do it. This is one way of it. Suppose you want to update it. What is the difference between segment tree and binary tree? Binary tree has no relation with the kind of problem you're solving. Binary tree is a data structure which only tells you what are the components it provides. A binary tree starts with a root. If it is, yeah, definitely, like we usually call it rooted. So it will have a root, and every node has 2 children or 1 children or no children. And when we come to segment tree, we assign a definition to it that now we are interested in focusing on every segment. And every node in the segment tree actually represents a segment. The root represents the total span of the array. And whenever we are going to the lower levels, every node represents some subarray of our array. And it stores some information for the entire subarray for which I don't need to visit the children. That is basically the idea of segment tree. So a binary tree where every node represents some segment of the array, that is basically segment tree. Does that answer your question? So in terms of implementation, it won't make sense to compare them, but segment tree uses the concept of binary tree, and it is meant for a certain set of problems, while binary tree is much more in general a concept. Great. So where are we now? We know ID, we know we need LID and RID. Suppose now I say, okay, great. Now I say that okay, I'm going to update something. So this is ID, this is the X value or the ID of my current node. For the time being, let's say that it is defined. something is defined. We will say we are concerned about some position. We are doing a point update, so this is the position, this is the val that we want to add, and then we have some L and R, which again you can say TL, TR or whatever. This is basically what this node, which we are currently existing. This is like yeah, the boundaries of this node, that is TL and TR. I think this much is sufficient, so let's see how we can proceed. The first thing is that we have to see if it is at all important or not. So if we see that TL is greater than pos or TR is less than pos, we can say that return what? Return ID. This is a difference we are bringing in. We are saying that whenever we are coming to a node, we will come using its ID and then it will return its new ID. Why? It may happen that we have come somewhere where it is null currently. So we will create a node and we will return the ID. So this is the usual practice. So we'll be returning the ID. It may be null, it may be something else. So we'll be returning the ID. There you go. Now what we'll say is that if the ID does not exist, we'll create an ID right away. ID equals to something like plus num. What is num? Basically some global variable int num which started with 0. So now what we are doing, we are basically assigning some values to these IDs. Do we get CP questions based on segment trees? A lot, quite a lot. And segment trees, actually, if you make it a habit to solve some segment trees for practice, you will actually see some problems are solvable without segment trees, but you will feel that with using segment trees it is far easier. Okay, sometimes the implementation becomes complex, but if you make it a habit, sometimes you will feel that a segment tree will make it simpler than other data structures. So ID equals to plus num means that now whenever you will come to this particular node, it will tell you this particular value. This particular value will be stored in ID. What does this check? Whether the value of ID is 0 or not. Not of ID means if it is 0. Now you'll do something like this, that if L is equal to TL is equal to TR. Great. So if TL is equal to TR means it is a leaf. If it was not created, I have created it. That is why I have written it above. So then you should update it over here. You should say that, okay, my tree or whatever. What did I create? I think tree of TL or TR. Either you can write that is equal to. I'm sorry, not tree of TL. It is basically tree of ID equals to. Lazy propagation is already covered. Yeah, I have covered it towards the beginning of today's class. Okay. We'll probably solve some problems tomorrow on lazy propagation, but the concept has been covered. Tree ID is equal to, or yeah, it's equal to val. And this is independent of whether this ID has been created now or before. It's nowhere related. Then what we say is, then what we do is something interesting. I will write that over here. What we say is that if it is not the case, if it is the case, then do return it. I don't want to proceed later on. Otherwise, we are going to do something like this. Int TM. TM I'm not writing it. TM basically refers to the middle node. So we will say L of ID equals to update. Don't look at the LHS first. First look at the right hand side. Update. I'll send LID. I will say this is the ID of my left node. And the position that I have to update is something like this, pos val. And we have something like this, TL, TM. Similar to as we had before. So what are we actually telling? That go to the left node, try to do the thing that I've tried to do in this particular function. And then when it returns, then take the original ID, like take its ID. So we can have, like it actually has to return its ID. So this also actually shall get the ID of the left child. It will store it over here. So now we have the proper ID. So L of ID, basically this is my ID. What am I doing? I'm calling the left child. That is going to return its own ID, which is a different ID. and it is going to return it, and basically L of id is going to store over here. L of id is going to store this value. Hope it makes sense. Next, the same thing we are going to do with RID. We are going to say update, call some update operation on RID. We have pos, we have val, we have tm plus 1, we have tr, and then tree of id is nothing but summation of these two values. So if it is not defined, or maybe how can we say, okay, tree of 0 is 0, we know that, so that is the way we can actually write it. Tree of lid plus tree of rid plus tree of rid. This is a combined step. Any doubts? Anything looking complicated? And then we'll return id. Take your time, try to understand it. अब अगर ऐसा हुआ कि इसके लिए एग्जिस्ट नहीं करता कुछ, देर इज लाइक दिस नोड डज नॉट एग्जिस्ट, व्हाट विल वी से दैट आवर आर आई डी वैल्यू इज इक्वल टू 0. So when we do tree of RID, what will we get? Tree of 0, which is 0. Tree of 0 will maintain as 0. And that is why we are doing plus plus num, so that our first number starts with 1. And hence when we'll get this over here, we can say 0 plus this basically gives us this node's value. If both are non-zero, then we can basically get the summation. Does this make sense? Does this make sense? So hope it does. If you have to query, similarly you can go like when you go to a certain node, if you see that okay, this node is not defined, if you come over here, then just return 0. That is the query part. Do you teach C language too? Usually no, I have not taught any language. I have taught in C language, I've taught certain algorithms in C language, but to be honest, I'm not an expert in any language because I've not spent much time. There was some time in my college where I focused on those things, but then I definitely did not delve into much depth. So yeah, talking about the query part, query will do what kind of a difference? It will not create any new node, it will not return an ID, it can be totally void. And what it will do is if nothing exists, then return 0. From me you can get nothing, from my children you can get nothing, simple as that. I wanted to learn sum of swap digits in C. In C, sum of swap digits. I'm not sure. I'm not sure about if it is a classical problem. I've not heard it. So anyway, but it will not be a problem. If it is a general problem, then we can discuss it in any language. Even this problem, it can work equally in C as we are doing in C++ and Java. Anyway, what else? Even over here, we can use the query thing. Over here, we can say that, okay, if this is the case, then return 0. We can return 0. This is basically how it works. Okay. And we are also calling if RID and LID are beyond our range, then also we are calling. And because we are always returning ID wherever we are, so we are never losing the value. Okay. So anyway, if you have any questions, it would be interesting for me to answer. But if you don't have any questions, I think we can move ahead because it's already 1903. Because we have started late, I'll be continuing probably up to 1940 or 1945 at max. And today actually, apart from this, I wanted to cover certain other things, quite many other things. But anyway, if we cannot cover merge sort trees, we'll take that tomorrow. By the way, only one thing is missing, which is the ending brace. This is where the ending brace is. Okay, looks good, I guess. Can we proceed? Would you like to have some poll questions to see if you can answer some conceptual questions, short conceptual questions? Would you like that? Then I'll probably discuss that, otherwise I'll leave it. Should I discuss some? Okay. So I had in mind something from yesterday. Okay. So suppose you have to do something using segment tree. Basically, what you need to do is the update part is point update, where you need to say that okay, at any position, a of pos is going to be equal to val, and you don't have to use uh, high. So you don't have to use sparse segment tree. N value is pretty low, 10 to the power 5. But for L2R, you basically need to find out the second maximum value. You have to find out the second maximum value. So what do you need? Games and tutorials, prefix sum. I'm sorry, that's your name, games and tutorials. Prefix sum, using prefix sum, we have discussed yesterday why we can't do the problems of segment tree. Updates and these queries together are difficult to be done, both in optimum time. Suppose I want to find out using segment tree to make it much more direct a question, that what is the second maximum in this range? What shall be what should you store in every node? This is something that we were discussing towards the end of previous class. What should we store in a node to make our working easier? Pretty easy question, try to answer it. I want to find out the second maximum over here, or maybe second maximum over a certain set of nodes. So what should I store in every node in the segment tree? Any ideas? Even those who have joined the class very recently, you can participate in it. So the precise question is, what information do you need to store in each node? What information needs to be stored in each node? Can we store only the second maximum? Will that help us? Shall it help if we store only the second maximum at each of the nodes? Suppose I come to know that okay, this is one node and this is another node which lies in the range. I just have to combine these two values. So what if I store, I can get the second maximum over the two nodes, over the union of the two ranges. Any idea? Okay, think about it. Meanwhile, the second question is, let us focus on this implementation. Uh, this particular implementation, maybe this build function is sufficient. You can put down your answer for the first question as well. This implementation is sufficient to answer this. Every segment, if I ask, is every segment some power of 2? In a segment tree, can we say that every segment is a power of 2? Consider this implementation. So we are going to call this in the manner build of n will be basically the first index and b will be 0 and e will be the last index. Okay. So is it necessary or can we guarantee that every segment, the size of every segment is a power of 2? What I mean by a segment is how many nodes exist from B to E. So when I'm going to call LC or when I'm going to call RC, they also need to be satisfied with it. And this actually, like, maybe for some last node you can forget it, maybe for some last node, but for all the previous nodes this should hold. So what do you think? So the previous question what I asked was, if you have to find the second maximum over given ranges in given queries, and then what should you store in every node? That is the first question. Second question is, according to this implementation that you can see, as well as the implementation that I had shown yesterday, according to either implementation, is every segment a power of 2? Yes or no? Any doubts with the questions? Or am I missing some chats? Let me check. Cool. So you can think it at your free time, because poll questions are not supposed to be one way. There is one last question. If you are interested, you can think. It's democracy. No one is going to force you. So suppose you have, this is a pretty easy question, but again, just to make sure that you are understanding something. This is a segment tree which has these many leaf nodes 0, 1, 2, 3, 4, 5, 6, 7. And now if you have to find the sum of the nodes 1 to 5, how many nodes will get involved? How many nodes will rather contribute to the sum? How many nodes will contribute to the sum? When I say contribute to the sum, I mean that you need to consider their values for finding your sum. If you don't get their values, then you cannot find the sum. How many nodes shall contribute to the sum? This is the third question, third poll question. I've got some update. I've got some basically uh, action item kind of a thing that I should be raising poll questions. So this is the last poll question. After this, maybe by 1914, we'll be moving to the main problem. So if you want a discussion on either of this, you can pitch it up, else we can move on. It's a matter of democracy, no one is going to force you. Similarly, you can also think in terms of updates, that if you update a certain node, or maybe update a certain range, if you want to update a certain range, how many nodes are going to be affected according to a particular coding implementation. For example, the coding implementation we took today. Okay, so looks fine. Okay, let's wait for another half a minute. You can ask any questions based on these questions. Else, if it is clear, ignore it. Okay. So now we come to our next problem, which goes something like this. Again, n and q, they all have the same characters. N is less than equal to 5 and q is less than equal to 5. Forget about that sparse segment trees. Basically, if this rises, you have to apply either coordinate compression or smart segment. What was that? Um, Sparse segment trees. But anyway, other than that, now the query nature is changing. On one hand, you have to update, which can be again point update or range update. So update can be again, how to play with both. It can be either point or range. That is not our focus. But our query is something like this. We have to find the minimum index, j belonging to LR such that a of j, so you have to tell which is the first index in this range, such that a of j is greater than equal to some given y. So some y will be given per query. You will have something like 2 space l space r space y, 2 l r y. This is the structure, and you have to tell this, and -1, return -1 if does not exist, -1 if none. So this is relatively an easy case. You can actually see that anyway, yeah, there can be many cases. So try figuring out how can we query this. How can we, like, what will be the structure of our query? How should we go about this? In every range we are asking the minimum index. So how should we query it? Think for a minute, and this is the time for questions. Pitch up any questions that you may want. Okay. So basically, what do you need to do? You need to do something like this, that when a node is fully covered, you can check whether it lies there or not. Yeah. So you can check whether it lies in. Basically, you can have all the elements in sorted order, maybe, or no. You can basically have the maximum element, right? You can basically, like, what kind of segmentary can you use? You can use a max segmentary for this question, right? What will that indicate? That in a certain subtree, will you ever find any value which can satisfy your requirement? So you can find that from here in using a max segmentary. So how can we, just a second, yeah. So how can we maybe proceed? We can proceed in this manner. We will tell, now suppose like the update operation is not a problem. The query operation is what we are interested in. When you think about it, you may have certain doubts and confusions. So basically, logically, what should you require to do? Suppose I ask you, in the entire range, I ask you, which is the first index where you are storing something. Now, this is interesting to observe. I want to find the minimum index where this is greater than equal to this. You cannot store something readily in the segment tree. That is why this question is a tricky question. I'm storing maximum max segment tree. Why? Because the nodes will give me an idea of in which direction I should proceed. So if I see that okay, I want over the entire range, and this node tells me that yes, my maximum is greater than equal to your requirement. So if my requirement is some y, it can tell okay, I have something greater than y or greater than equal to y. And I can say okay, you don't need to visit this part. This part can be totally cancelled. You can totally focus on this part. You can go and see whether this is the node or this is the node. You can go down and see. Max segment tree, when we are storing it, we don't have the information that which is the node that we are interested in, or basically which is the node that contains it. Similarly, if it happens that okay, this node tells me that okay, my maximum value in this subtree is going to be less than y, it is less than y, what can I say? Just forget this entire subtree, focus on this one. So can you see the binary decision that we are making? In the face of any requirement, we are always getting the the provision of making a choice between our left subtree and the right subtree. What is the time over here? Okay. So yeah. So can you see how we can actually bring that to our benefit? We know always we have to go to either direction, either to the right or to the left. And hence, that's it. That's how we can proceed it. So if we want the coding implementation goes something like this. You have a query part, you have these things, x, int tl, tr, and you have something like int the y, this y. Now an important thing is that suppose that this is also partially covered and this is also partially covered. Then you actually have to reach to the depth of it to understand which one is important for you. You have to come up like above and you have to tell that okay, I can find or I cannot find. If you cannot find, you have to search again over here. That is a kind of repetition that we are doing. But basically from a node, definitely we are proceeding once, we are coming back, and then only we are checking whether we can get something or not. That's it. Any questions? Okay, so now what we can simply say is that at any node, suppose I have called this part and this part because they are sort of partially covered. If it is partially covered, it will call both the parts, else it might take the decision by itself, or it will be fairly easier. And then what it can say is okay, I've got some value from here, I've got some value from here, and then I can pick up the minimum. I can do something like that. What I can do is if this returns, like if this gets -1 or something like that, it can say okay, I've got some infinity. And then it can also take the infinity from this part, or maybe if it has got some positive value, maybe 5, it will say that okay, I'll take the minimum of them and I'll return 5. It's pretty straightforward. So if you have any doubts, you can ask. Okay, so let's proceed. I think this problem is clear. Let's proceed to the next problem. The next problem is a far greater a classical problem. Count the number of inversions in an array using segment trees. Over here you will actually find that finding the number of inversions using merge sort actually requires much greater number of operations, or maybe much more intelligence compared to using segment trees. Using segment trees you can actually skip many different things. It will be pretty straightforward. Count the number of inversions in an array. So this is around the second last problem that we are doing. After this we'll do the last problem for today, and tomorrow we'll be doing merge sort trees. Counting the number of inversions, it will be nice if you can present some ideas. We can take it from there. Do you have anything? How can we do the number of inversions? You just have to count number of inversions. You don't have to basically do the other things that we were doing in the previous problems. No updates, nothing. There is an array. You have been given the array. You have to count number of inversions and give it in n log n time. How can you do it? Can we say that it's pretty straightforward on the basis of whatever we discussed? Think about it. Suppose, let me just give you this kind of a hint, that you have stored these integers in the first few places, and then you're searching for this position. You want to see that, okay, for this position, whatever value is there, how many inversions will this value create with all the values that I have taken beforehand? Which are the positions, or what is the number of positions that will face an inversion with this value? Can you think of something? What is the kind of segment tree that we should use? I think that should precisely be the question. What is the kind of segment tree that we should use so that we can solve here? I see you have pretty much stopped talking. That's not good. But anyway, if I have the right to consider that I'm more experienced than many of you, then you are probably not using it to your advantage. You could have asked questions, you could have been more interactive, it could have helped you better. It's the same thing for me, however, the way I proceed. As per my experience, you're not using it to your full advantage. If I'm not wrong. If you are not aware of everything, then you are not doing the right thing. So cool. Number of inversions only means that if an element is lesser than any of the elements which are present before it, then that forms an inversion. This is basically what is an inversion pair. I hope you have seen the message. The notification is that this is a subscribers only mode. So if you only subscribe to the channel, then only I can view your message. So if you are trying without that, then I'm sorry, I can't view your message. So inversion pair is something like this, that if I is less than j and ai is greater than aj, what basically means is that some value is greater than some value which is present ahead of it, in front of it, then we say that forms an inversion pair. I hope I don't have to give examples for inversion pairs. Now when you have to count number of inversions, suppose you have stored all the previous elements, so for any element ai you can say that, okay, search the segment tree and find out from 0 to ai minus 1, in this range, what is the number of elements? What is the number of elements, or what is the frequency of these elements? So it will basically be like, suppose I say that ai is less than or equal to 10 to the power 6. You just have to maintain the sum of frequencies of these elements, right? So whenever an element comes, you just have to store it in the segment tree, and you have to increment its frequency by 1, and that's what the segment tree will tell. If a segment tree indicates some range TL to TR, then that means that whatever value occurs within this is exactly the number of elements from TL to TR. So whatever elements have been taken as input till now, which are greater than equal to TL and less than equal to TR, then the value is V, which is stored within this. Okay. And yeah, there are no range updates as such. We have only point updates, which is just add a certain value. So not a problem for us. We can actually, from this particular question, we can figure out what will be our query operation, what will be our update operation, and then it will be a simple use or implementation of our segment tree. Hope that makes sense. So it will be like, the query will be pretty straightforward. The query will be something like this: 0 ai minus 1 L or TL, we can say TR. Yeah, that's it. I think the X is also supposed to be there. And what else? Yeah, and update operation, which will take place after the query operation. This is going to be, or this can take place even before the query operation, that we want to update, add the index AI, and we want to add one, so it can be a kind of sum segment tree. I want to add one at this particular index, and currently I am hovering over the range TL to TR, and this is the particular index of the tree data structure, or the array data structure, the array tree basically, on which I'm working. And yeah, we are done. Query and update, both are sorted. Any questions? Okay, I think how much time is left? Alright, according to this, only a few minutes are left, but I don't remember. Anyway, we can maybe informally discuss the next topic. We won't go into the coding details maybe. If you want, we can, else we will not. I'll just discuss it shortly and then I'll leave it. Final problem for today is, we want to basically do a kind of point update where we say a of pos is going to be equal to val, okay, and we are going to have a search query where we are going to ask a slightly different thing, that find the minimum I in no LR. You have to find out the minimum I such that summation of aj, where j ranges from 0 to I, is greater than equal to s. So some s will be given. So given s, you have to find out what is the minimum I such that the summation of these values, that is so that this particular, you have to find the smallest prefix of the array which will be greater than equal to, whose sum will be greater than equal to s, and it is also given that val is greater than equal to 0. What this means is that there is a monotonicity, implicit monotonicity. So how can we go about it? Let me check. I see. Okay. So the intuitive idea first of all is that if you have to solve it in a kind of array where I ask you the same question, that what is the best prefix for different values of s, you will do kind of binary search. So over here, because updates are taking place, the idea is to use segment trees to form the updates, and whenever you have to find the value of this query, we will do the query operation over the segment tree and try to find out from there. So now the question is, what is the cost of it? We know that we are only querying over some ranges. We'll only need to query over some ranges. How? We can basically say we need to find out some I, and for every I, what do I need? The summation from 0 to I. That is what I need. So we can get this I, we can get the best I. Now there are two ways in it. One thing you can do is you can do some range updates. You can go about doing range updates. So when you say I want to update one position, you can update the prefix sum from there till the end. You can actually make that update in the entire segment tree. If that is, I think was that, anyway, leaving that. So you can use prefix sums to ease out the thing. But if you're not using prefix sums, because that would bring in the complication of lazy propagation. Another way that you can easily do it, you keep it point update, and you will do binary search for finding the best value of I, that which is the best value, and for every value of I, you have to find out what is the summation. How can you find out the summation? This will be a simple query operation. Now we know every query operation is order log n, and we know how many times we will do the query operation for that many number of values of I which we choose to find out the final best I. So that many number of query operations will be doing. So what is the number of i's? Number of i's basically goes to log n. Again, number of i's, because there are n possibilities of I, so it goes to log n, and hence what can we say? That for every value of I, if we have order log n time that the query is going to take, so your total time complexity is going to be order log square n. Any doubt? So what this basically means is that our search query now becomes expensive compared to our point update. Point update is going to take the same log n, but search query is going to take log square n, which is not a good thing. Okay, this is not a good thing. And what I've done over here is nothing but a kind of explicit binary search. What I've said is I'll do binary search outside the segment tree, and on the basis of the result of binary search, I will ask the segment tree to find out the value for me. Whatever I value I'll get, I will request the segment tree with a query that find me the sum of this particular range. It turns out that it is due to the explicit nature of this binary search that we are actually forced to consume this extra complexity of log square n, where we could have tried something in log n, and hence we try to optimize it using the concept of implicit binary search. Implicit binary search. Implicit binary search is going to be pretty intuitive an idea. What we basically say is the binary search should occur within the segment tree. So what we'll basically say is that when we have come over here, when we know that the sum, this particular sum, is less than the target sum, then you can directly surrender. You can say that, okay, take me back. I can't actually include any of my children to support your needs. But if it says, okay, I can support it, now which of my children can help me support it? It can first query its left child that, okay, can you help me finish it? So it can ask its left child that, okay, try your tree and help me finish it. Left child will first say that, okay, mind you, my sum is nothing but my sum is something, sum dash. So if sum dash is less than y, then I can't help you. If sum dash is less than y, then I can't help you. If it is greater than y, then I can give it a try. But if it is greater than y, then I definitely can't do something. Yeah. Thanks, Umang. But anyway, where were I? Even I am tired because it has been a whole day for me. From morning I am doing something or the other. So yeah, what are we doing now? If the sum dash is lesser, we can directly ignore it. If the sum dash is greater, we can take it and we can explore over here what we can do from over here, what is the best I. Else what we can say is if this is smaller, we can say that, okay, consume this sum dash, and whatever your y is, impress that y minus sum dash upon the other node. Expect the other side, the right subtree, to satisfy the rest of your requirement. And why do you know that it can always satisfy? Because you always know that this node is capable of satisfying your need because this node has a sum greater than equal to y. आपको पता है कि जो रूट है वो रूट आपका greater than equal to y स्टोर करती है, आपने इनिशियली चेक कर लिया है. When you have checked it, now you only need to see whether your left subtree is sufficient or not. If it is not sufficient, focus on the right subtree. What information shall you use? When you go to the right subtree, tell the right subtree, I don't require everything from you. Left subtree will offer this, so just subtract this, and this is what I require from you, y minus sum dash. Makes sense? So that is like exactly what we were trying to optimize and what we end up optimizing. This is the final application of implicit binary search. Any questions? So since we have already run out of time and you have something related to snack down coming up at 8 o'clock, so for those of you who will be interested in both the things, I would say now let's leave some time for the next. Tomorrow we can stretch this discussion. We can discuss on other things, specifically problems. I wish to discuss on merge sort trees. If you have any doubts regarding any of these things, though usually you all don't have any doubts, you can ask. But else, I think we can call it a day. I can wait for 1 more minute. If you have any questions, you can ask. So today we have discussed lazy segment trees. We have then visited certain problems. We have discussed coordinate compression and sparse segment trees. We have discussed binary search on segment trees, both explicit and implicit. We have covered certain classical problems like number of inversions in an array. So yeah, if you have any questions behind any of these, tomorrow you can pitch up the questions. Okay? Tomorrow is our last class so far as I know. If it gets extended, if the series gets extended, that is a different thing. But anyway, so yeah, good luck with your endeavor. Take care. Keep coding. Bye. What is a persistent data structure? Persistent data structure is one that remembers what you had stored beforehand. So one meaning of persistence is basically that it will remember whatever you want it to remember, and especially for in terms of what GitHub does, what many other data structures are known for doing, persistent data structure is one which will basically store the previous versions as well. So if you are changing something, it will not only store the change, it will also store the previous version of the change. Does that help? So you can visit, like you can imagine the same thing for persistent segment tree, persistent, I don't know, linked lists, definitely. They are existing, they are very common. So, cool. I guess that helps. Take care. Good luck. Bye. Good night.